So we go on to question 6, the last one in tutorial sheet 3, I think. So now we're being told a speedboat increases its speed uniformly from v naught or vi, v initial equal to 20 meters per second to velocity final 30 meters per second at a distance 2.00 times 10 to the power 2 millimeters. So A is telling us to draw a coordinate system for this situation and label the relevant quantities including vectors. So then for A, we'll be told to draw a coordinate system. So just given the velocity, so you can say this is the velocity in meters per second. Then we're going to say this one, let's put our velocity, let's put this as our distance. So we're going to put this one as our x distance in meters. So we're going to have something like this, yeah. So then you can have that for the velocity in meters per second. So now we are going to have this boat, speedboat. So you have this boat here, a rough sketch of a speedboat. So it's going to be going, and it has a capacity. So it's going to be going this side at 20 meters per second. Then over a distance of 2 times 10 to the power 2 meters, is going to now accelerate to a speed of 30 meters per second. So now these arrows, they are just labeling the vectors to say they are going this side. So then for part B, they are going to be told for the given information what single equation is appropriate for finding the acceleration. So when you look at your equations, your kinematic equations, I think you have got v is equal to u plus at x naught is equal to x final is equal to x initial plus v naught t plus at squared. This here is half. Then we have got v squared is equal to v squared naught plus 2 s, where s is the distance. So for me, I think the one that can work here is, well, this one can't work because it has time and we don't have time. This one cannot work also because it's telling us to find time. Although if we are told to find equations that can work, we can use this equation, we can use these two equations, and then make all of them subject, make t subject to a formula, and then equate this t to that one. But then we're being told to find a single equation. That's most, and then most is the other way that we're going to check out. Then when you look at this one, it has acceleration, yes, it doesn't have time, and it has the distance, and of course we have the distance, which is this one. So as we can say, v squared is equal to and it's not necessary to write all this, by the way. You just have to write the final one, which is v naught squared plus 2a. Some can say s as delta x, which is the same as x minus x initial. Then we go to C. Using this same one, solve symbolically for the boat's acceleration in terms of v final, vi, and delta x. So I'm being told to find for v final, vi, and delta x. So now here we must have our acceleration as the subject of the formula, and then on the other side of the equation we must have things like this. Okay, so now let's start. So this one is our v final squared is equal to this one is our v naught, vi squared, then plus 2. We have our a and our delta x. So now here we will not use this one because we're being told to say we must have delta x. So then taking this one that side, we're going to have v final squared minus vi squared is equal to 2a delta x. We divide both sides by 2 delta x over 2 delta x. We're going to have a being equal to velocity final minus velocity initial, all of them squared over 2 delta x. And then we've solved. And then in part D, the paper is done, I think we can go to the other one. So we're going to start from there. Then we're being told to say in part D, substitute the given values of that substitute the given values obtaining that acceleration. So now our acceleration, when you substitute the values, is going to be a is equal to the velocity squared, the velocity final, this one is final, that's 30 squared minus 20 squared over 2. Delta x is just the distance, which is 2 times 10 to the power 2. Here acceleration is going to be equal to we say 30 to the power 2 minus 2 minus 20 to the power 2 divided by 2 times 2 exponent 2. This one will give us 1.25. 1.25 meters per second squared. And then now we go to E. This was our D. We go to E. Find the time it takes for the boat to travel at a given distance. So now we go back to these equations. We'll check out which one can work, and then according to me, the best one that would actually use, I think, is this one, because it's less complicated. We can use this one as well, but let's just use this one. That's V. V is equal to U plus AT. So now to find the time, we're going to have V minus U is equal to AT. We divide both sides by A. We're going to have our T being equal to V minus U over A. So T is going to be equal to, our final velocity is 30, our initial velocity is 20, our acceleration is what's our acceleration? Our acceleration, we found it, 1.25. Found it. T is going to be equal to 10 divided by 1.25. T now is going to be equal to 10 divided by 1.25. That's going to be 8. Oh, I punched this in the calculator, by the way. 10 divided by 1.25, that's 8. So 8 seconds. Thus we are done with question 6. We go to the last one now, question 7.